Yes, sir.
Okay.
Yes, sir.
So, uh, so you have a Bessel's function, your Legendre differential equation, Bessel's differential equation, Hermite differential equation, Laguerre differential equation, and other special functions in the first part of your unit 1 and the last 2 units. So, in the previous class, we have discussed about partial differential equation, how to solve partial differential equation with separation of variable method. So after that, we will discuss some special functions. Why it is called special functions? Because an ordinary linear homogeneous differential equation with constant coefficients can be solved by using your separation of variable. There are a number of methods which can be used by you to solve it. But when your coefficients are not constant, they are either variables of x or y or something else, then the traditional method is not will not work to solve those type of equations. So the differential equations with variable coefficients encountered in physics and engineering could be solved by a special technique called power series. So some of the examples of such type of equation are Legendre differential equation, which can be read as 1 minus x square y double dash, that is d square y by dx square, minus 2xy dash plus L into L plus 1 y is equal to 0. So see, the coefficient of y double dash or d square y by dx square is equal to 1 minus x square. So as x is a variable, so the coefficient is variable. Similarly, the coefficient of dy by dx is minus 2x, which is a variable. Similarly, another differential equation is your Bessel's differential equation. X square y double dash plus xy dash plus x square minus k square y is equal to 0. So see, here y, the coefficient of y double dash or d square y by dx square is equal to x square, which is a variable. Similarly, the coefficient of y dash, that is dy by dx, is equal to x, which is a variable. Similarly, the coefficient of y, that is x square minus k square, that is also a variable, as it is dependent upon the value of x, which is a variable itself. See, another special differential equation is your Hermite differential equation. Y double dash minus 2xy dash plus 2 alpha y is equal to 0. Here, the coefficient of y dash is a variable. Similarly, Laguerre differential equation, xy double dash plus 1 minus xy dash plus alpha y is equal to 0. Here, the coefficient of y double dash is equal to x, which is a variable. Coefficient of y dash is equal to 1 minus x, which is a variable. So I have earlier said that this type of equation can often be obtained in terms of power series. These series are usually not elementary or transcendental functions. On the other hand, the lead to the higher transcendental functions are so-called special functions. So these type of functions are usually called special functions. So what is a power series? The power series is used to solve this type of special functions. So let us have an idea what is a power series. The sum of an infinite number of terms of the form a0 plus a1 multiplied by x minus x0 plus a2 multiplied by x minus x0 square plus so on and so forth can be written as summation n is equal to 1 to infinite an multiplied by x minus x0 to the power n is called a power series in x minus x0. The coefficients of an and the center of x0 of the series are constant independent of the variable x. So in this type of functions where there is a series form x minus x0 to the power n, power of a series. So if you put n is equal to 0, that is a0 x minus x0 to the power 0, n is equal to 1, a1 x minus x0 to the power 1, so on and so forth. So here there is a region where this function is solvable, and this function has a real solution. So the center of that region is called x0, and the coordinates of x0 will be the coordinate of the center of that function. And the equation becomes modified when you put x0 is equal to 0, which is the simplest case. If we put x0 is equal to 0, that is the center of that power series will be the center of the coordinate axis. Then we can have a0 minus a0 plus a1x plus a2x square plus so on and so forth. Look, your x0 is taken as 0, which is the simplest case. And if x0 is equal to 0, then x minus x0 will be x. So your original equation 3.1 will be modified as a0 plus a1x plus a2x square plus a3x cube plus so on and so forth, which is equal to summation n is equal to 0 to infinite an x to the power n. This is a power series in x. The original one was the power series in x minus x0. And it is a power series in x, which is the simplest case of x minus x0, where x0 is equal to 0. So by shifting the origin, the coordinate system, which is equivalent by replacing x minus x0 to by x. So initially, the origin is at x minus x0. Now the origin is at x0. Just we have shifted the origin. One can arrive at the equation 3.2 from equation 3.1. So it is sufficient to discuss the properties of power series of the form given in equation 3.2. The exponents of a power series are non-negative integers. The exponents of power series are non-negative integers. That means your summation n is equal to 0 to infinite n x to the power n. In this expression, x to the power n. So n in the x to the power n term is non-negative integer. It can never be 0. It can never be minus 1, minus 2, minus 3, minus 4, any negative number. It can never be 3 by 2, 5 by 7, 7 by 8, 9 by 11, like this of fractions. It is always positive integer, either 1, 2, 3, 4, 500, 10,000, 1 lakh, like this. So some of the examples of power series are 1 plus x square plus x cube plus so on and so forth. This can be written as summation n is equal to 1 to infinite x to the power n. Similarly, another power series is 1 plus x plus 2 factorial x square plus 3 factorial x cube plus so on and so forth. This can be written as summation n is equal to 0 to infinite n factorial x to the power n. Another power series is 1 plus x square by 2 factorial plus x cube by 3 factorial plus so on and so forth is equal to summation n is equal to 0 to infinite x to the power n by n factorial. These are the examples of power series. If any term of the series has negative or fractional powers, it cannot be a power series, which I have already explained. For example, your 1 by x plus 1 plus x square plus so on and so forth. Here, the first term is 1 by x, that is x to the power minus 1. So as there is a term x to the power minus 1, this can never be a power series. Similarly, x to the power half plus x to the power 3 by 2 plus x to the power 5 by 2. This cannot be a power series because the powers are not integers. They are half, 3 by 2, 5 by 2. These are not this power series. These two are not power series because they have negative and fractional powers respectively. Okay. So now you have discussed what is a power series. So power series is in the form summation n is equal to 0 to infinite n x to x minus x0 to the power n. It can be written as n is equal to 0 to infinite n x to the power n, where the origin coincides with the center of the power series. So now the next thing is convergence of power series, whether the series converges or diverges in a region. So you know convergence means all the points comes to one point, and at that point we say it is convergent. So a power series summation n is equal to 0 to infinite n x to the power n is said to converge at a point x on the interval I if the limit n tends to infinite summation n is equal to 0 to capital N x to the power n exists for all x in I, all x in the interval capital I. Otherwise, the series is divergent or the series diverges at that point. Okay, I think you get it. Here, the summation n is equal to 0 to capital N to the n x to the power n is called the nth partial sum of the series. Okay, so this term is called nth partial sum of the series. When the series converges, the summation n is equal to 0 to infinite n x to the power n is equal to fx is defined on I, and the series summation n is equal to 0 to infinite n x to the power n is called a power series representation of the function fx. Okay. Next is radius of convergence. What is the region where the power series has a solution? So radius of convergence decides the regions where the power series converges. Radius of convergence means there is a radius and you plot a circle, and in the circle the power series converges in any point in the circle. For each power series, summation n is equal to 0 to infinite n x to the power n, there corresponds to a real positive number capital R such that the series converges if modulus of x is smaller than R and diverges if modulus of x is greater than R. The number R is called the radius of convergence of the series. Suppose you assume a number R, capital R, and that R is the radius of a circle. So if R is the radius of a circle and your x in the power series, it is smaller than that R, either x or minus x is smaller than that R, then it is converges, it is convergent or it converges at that point. If x is greater than R or is equal to R or minus x is equal to R or greater than R, then it cannot be, it may or may not converge. And in case of x is greater than R, it never converges. And in case x is equal to R, then that at that point x, the series may converge or may not. So imagine a circle. Inside the circle, at all the points, the series converges. On the periphery of the circle, the series may converge or may diverge. And outside that periphery, at all the points, the series diverges. Okay, you got it? So the next question is, how can we evaluate that R, radius of convergence? So when you evaluate radius of the convergence, then you can decide at a certain point whether the series converges or not. The radius of convergence of a power series can be determined from the coefficients of the series by the formula R is equal to limit n tends to infinite modulus of an by an plus 1, n subscript n plus 1. This is equation 3.3. So if you have n, then you can find out an plus 1, and by dividing these two terms and having the modulus and limit n tends to infinite, you can have the value of R. So there are three cases. When x is equal to R, when x is equal to R, then you can say it may converge or may not. So if R is equal to 0, the radius of convergence is equal to 0, then what you will get? Then x is equal to 0, and it diverges for all other values except x is equal to 0. So at x is equal to 0, the series converges, and at all other points, the series diverges. So the series n is equal to summation n is equal to 0 to infinite n factorial x to the power n is such type of series where the series converges at one point, that is x is equal to 0, and at other points it diverges. If 0 is smaller than R, smaller than infinite, R is between 0 to infinite, then the series converges if modulus of x is smaller than R and diverges if modulus of x is greater than R. And the third case, when R is equal to infinite, the value of R is equal to infinite, then the series converges at all points, because R can be any point between 1 to infinite. It can be 1, 2, 3, 1 lakh, 1 crore, so on and so forth, 10 to the power 7, 10 to the power 8, so on and so forth. So if R is greater than 0 and smaller than infinite, then at all points in the region, the series converges and diverges only at R is greater than infinite, which is not a valid case. Yes, the series n is equal to 0 to infinite x to the power n by n factorial is this type of series. Okay, so there are some examples. You may work out it. The radius of convergence for three series. For the first case, you have R is equal to the original power series is n is equal to 0 to infinite n plus 1 by 3 to the power n multiplied by x to the power n. So n is equal to how much? N is equal to n plus 1 by 3 to the power n. Similarly, n plus 1 is equal to how much? Just put the value of n plus 1 in case of n. So you will get n plus 1 by 3 to the power n plus 1. And divide these two. You will get limit n tends to infinite n plus 1 by 3 to the power n whole divided by n plus 2 divided by 3 to the power n plus 1. And you will get limit n tends to infinite 3n plus 3 divided by n plus 2, which is equal to limit n tends to infinite 3 plus 3 by n divided by 1 plus 2 by n is equal to 3. Are you getting it? So the series converges at all points between 0 to 3. So minus 3 smaller than x smaller than 3. This is the region, and it diverges for all values where the value of x is equal to greater than 3. Similarly, there is another 2 examples. You may go through it. In the second case, the series converges for all x and is equal to an exponential factor e to the power x, because your radius over convergence is equal to infinite. For the third case, the series converges only for x is equal to 0 and diverges for all x is not equal to 0, because r is equal to 0 after you work out the problem. Then what are the properties of power series? In power series, you can differentiate and integrate it term wise. Suppose you have a0 some plus a1 something plus a2 something plus a3 something, so on and so forth. Then if you differentiate it, you have first differentiation of a0, then you have differentiation of a1, that's something, differentiation of a2, that's something, so on and so forth. If you integrate it, then you can integrate a0, then integrate a1, that's something, a2, that's something, so on and so forth. And after that, after you get the differentiation and integrate it, you can add it just algebraically, and you can get the solution of that power series. So it can be term wise differentiate and term wise integrate. Second, it can be term wise added and term wise subtracted. So term wise addition and subtraction is possible in power series. You can go through this lecture. And then third is term wise multiplication and division. If fx is a power series, gx is another power series, then you have fx dot gx, which can be written as n is equal to 0 to infinite cn x to the power n, where cn is equal to a0 bn plus a1 bn minus 1 plus so on and so forth n b0. And this is also a power series. This can be term wise multiplied and term wise divided. If fx and gx are two power series, then fx plus gx is another power series. Fx minus gx is another power series. This can be added term wise and subtracted term wise. Similarly, product can also be also converge for x in an interior of an interval of convergence, and fx by gx is also a power series subjected to the condition that your denominator is not equal to 0, that is b0 is not equal to 0, because all other terms contains x square and so on and so forth. So if b0 is equal to 0, the denominator will gx, if b0 is equal to 0, then it cannot be a power series. If b0 is non-zero, then fx by gx and the expression shown in the text is a power series. However, in some cases, the quotient f by g may not converge at some points where both the series fx and gx converge. For example, both sin x and cos x are examples of a power series where sin x by cos x is equal to tan x converges only at all points except modulus of x is equal to pi by 2, because tan pi by 2 cannot be defined and it tends to infinite. So sin x is a series that converges at all points. Cos x is a series that converges at all points. R is equal to infinite for these two series. But division of sin x by cos x, you have the tan x that is that converges only at certain points, except that the modulus of x is smaller than pi by 2. Then your identity principle. What is identity principle? Suppose you have two series, n is equal to 0 to infinite n x to the power n, and another series n is equal to 0 to infinite bn x to the power n. Then suppose these two series converge to same function as modulus of x is equal to r. So the suppose in the first series and second series n and bn, your radius of convergence is equal to capital R, and they are same. So in that case, you have n is equal to 0 to infinite n x to the power n is equal to n is equal to 1 to infinite 0 to infinite, read it 0 to infinite bn x to the power n, and n is equal to bn for all n greater or equal to 0. So here n is equal to bn. If both the series contains same limits in the summation and the both series have same radius of convergence, then n is equal to bn, and your n is greater or equal to g. For n is greater or equal to 0, n is equal to bn. Then vanishing of all coefficient. Identity principle means all the terms have same value. Then vanishing principle means all the terms have 0 value. So suppose fx is equal to n is equal to 0 to infinite n x to the power n is equal to 0 for all modulus of x smaller than r. Then all the coefficient vanish identically. That is n is equal to 0 for all n greater or equal to 0. So all the values, that is a0, a1, a2, a3, a4, all are 0. That are vanishing coefficients. This happens only when fx is equal to 0. In the series n is equal to 0 to infinite nx to the power n. Then another important thing is shifting the index of summation. In an infinite series, summation n is equal to 0 to infinite nx to the power n. The index of summation can be shifted by a number k. That can be shifted by a number k, where n can be written as n plus k, and decreasing the starting point by k. For example, summation n is equal to 3 to infinite nx to the power n minus 1 can be written as n is equal to 0 to infinite. Look, your n decreases from 3 to 0. Initially it was 3, now it is 0. And you see your n is changed to n plus 3, and x to the power n minus n is changed to x to the power n minus 1 plus 3. So summation n is equal to n is equal to 3 to infinite n x to the power n minus 1 is equal to summation n is equal to 0 to infinite a n plus 3 x to the power n minus 1 plus 3, that is x to the power n plus 2, where the summation index is increased from n to n plus 2, and the starting point is decreased from n is equal to 3 to n is equal to 0. Similarly, summation n is equal to 1 to infinite n x to the power n minus 1 is equal to summation n is equal to 3 to infinite n minus 2 a n minus 2 x to the power n minus 3. Okay, x to the power n minus 3. So this, like this, you can shift the indices of the summation. Are you getting it?
Okay.
Hello.
Hello, hello, sir. Is the meeting still on or it was concluded? Actually, it's not audible and it's confusing also. We are not getting actually whether the meeting is still on or it was concluded.
Also not clearly audible, sir.
କ୍ଲାସ୍ ହବ ନା ଏଇଠୁ ବନ୍ଦ ହେଇଗଲା?
Technical problem ଅଛି ବୋଧେ ନା କଣ?
କିଛି ଜାଣି ହେଉନି।
You are left to midway, I think.
क्या हुआ? कुछ टेक्निकल इशू हुआ?
Actually, Gauri sir left his agency.
ओहो,
लगता है आज क्लास नहीं होगा।
मेल दे दियंतु कालिका मेल दे दीजिए। कल का जो मेल आया था उसमें क्लासरूम अच्छे भुवनेश्वर में सब एक एक तो रिप्लाई आ सकता है सर।
कोई बता सकता है आज का जो टॉपिक पढ़ा रहे थे, जो पावर सीरीज वो किसका है? मतलब वन का है या टू का है एमपीएच का?
बेसल फंक्शन वगैरह था, मतलब ये वन का ही है मैथमेटिकल
मैथमेटिकल फिजिक्स
का ही है, ये मैथमेटिकल का ही है
वन
एमपीएच
का है
001 का।
यूनिट 3।
मैथमेटिकल फिजिक्स MPH-1 का
वन
बाद में MPH-4 ही
वन
डिस्कशन।
का है यूनिट 3।
ବହି କଣ ସବୁ ଆସିଲାଣି?
ବହି ସବୁ ଏକ୍ଜାମ ପରେ ଆସିବ ନା।
MPH 2 ର ଆଉ 4 ର ଆସିଛି ବୁକ୍, ତିନିଟା ବୁକ୍ ଯାହା 4 ର ଆସିଛି, ଆଉ 2 ର ଆସିଛି ବ୍ଲକ୍ 1 ବ୍ଲକ୍ 2, 4 ର ଆସିଛି 1 2 3।
ମୁଁ ଟିକେ ଲେଟରେ ଆସିଲି ଭାଇ, ମାନେ କ୍ଲାସ ଆରମ୍ଭ ହେଲାନି ନା ସରିଲାନି ନା ଷ୍ଟାଟସ୍ କଣ ଟିକେ ଭାଇ କହିବେ?
କ୍ଲାସ୍ ଆରମ୍ଭ ହେଇସାରିଛି, 4ଟା ପରେ ଆରମ୍ଭ ହେଇଥିଲା, ବର୍ତ୍ତମାନ କିନ୍ତୁ କୌଣସି କାରଣ ମତେ ଟିକେ ଷ୍ଟପ୍ ଅଛି, ତ କେହି ଜାଣି ପାରୁନାହାନ୍ତି। ଯେ ସାର୍ ଲେଫ୍ଟ ହେଇଛନ୍ତି, ଟିକେ ଜଣା ପଡିବ ଏ ସମୟରେ।
ଓକେ ଓକେ, ଥ୍ୟାଙ୍କ ୟୁ ଥ୍ୟାଙ୍କ ୟୁ।
ଭାଇ ମାନେ ଏକ୍ଜାମ ପାଇଁ ପ୍ରିପାରେସନ କେମିତି ଚାଲିଛି? ସବୁ ଠିକ ଠାକ ତ? ପୁରା ରେଡି ସବୁ ଏକ୍ଜାମ ପାଇଁ?
ବହି ତ ଆସୁନି ଆଉ ରେଡି କଣ?
ଟପିକ ଯାହା ପଢା ହଉଛି ଜାଣିବୁନି କୋଉଠୁ କୋଉଠି ଆସିଛି ଭାଇ, ପ୍ରିପାରେସନ କେମିତି କଣ କରିବା?
ପ୍ରିପେୟାର ତ ଟୋଟାଲି କିଛି ହେଇନି, କିନ୍ତୁ ଏ ଇଗ୍ନୋର ବେଶୀ ସେଇ ଏସଏକ୍ୟୁ ଆଉ ଟର୍ମିନାଲ କ୍ୱେଶ୍ଚନ ଆସାଇନମେଣ୍ଟ ବି ପକାଏ କ୍ୱେଶ୍ଚନ ର। ଆଉ ଏଥର ତ ନୂଆ ହେଇଛି ମାନେ ଆସାଇନମେଣ୍ଟ ବି ପକେଇବାର, କିନ୍ତୁ ଟୋଟାଲି ଦେଖାଏନି, ବୁକ୍ ର ନେମ୍ ବି ଦେଖାଉଛନ୍ତି।
ସେଇ ତିନିଟା ହିଁ ଦେଖିକି ଯିବା କଥା ଆଉ କଣ, କିଛି ଉପାୟ ଦେଖାଯାଉନି କିଛି।
ସେ ତିନିଟା ଦେଖିବା ପାଇଁ ବି ଟିକେ ଅଣ୍ଡରଷ୍ଟାଣ୍ଡିଂ ହେଇଥିବା ଦରକାର ସେ ସବଜେକ୍ଟ ଗୁଡାକ, ଏମିତି ବି ଦେଖିବା କିସ ଦେଖିବେ।
Sir, please create a WhatsApp group that will help us to share information about classes, practicals, and other informations regarding MSc PH. Please create a WhatsApp group.
There is already so many WhatsApp group available there. The information that will be shared to all when there is something.
Madam, actually there is no official WhatsApp group. All the WhatsApp created by all the students, participants. And there are many WhatsApp groups, MSc PH BJP College, MSc PH MPC Autonomous, and already 2 group, MPH 001, again yesterday another group is created. So it is too irritating. If there is classes and they were shared PDFs, then only one group will be enough. For MPH 001 group, again MPH 002 another group. If this type of group continues, how can you share information? There are many groups. And practical schedule, I think it will be sent by regional center in the Bhubaneswar Regional Center website group. You can see there.
Okay, sir. Please, Bhubaneswar Regional Center group पे मुझे ऐड कर दीजिए प्लीज इस नंबर
Bhubaneswar
पे।
Regional Center website. Bhubaneswar Regional Center website, and other WhatsApp groups are created by the participants, not by the official holders, that is director
Okay.
or deputy director. Only official website IGNOU RC Bhubaneswar, you can see the practical schedule
Please add
when it
this
will be
number.
updated.
Please add this number. I'm messaging.
अच्छा सार मु पचार दबा जे प्रोबेबल क्वेश्चन कौन ए चैप्टर रो आसी परियो
Does anyone have a PDF of mathematical physics by Satya Prakash?
कहना हमें जानी जानती ना कौन क्वेश्चन आछो हमको दरकार क्वेश्चन दरकार
Hello friends, does anyone have PDF of mathematical physics by Satya Prakash?
No.
If anyone have, please share it in the Bhubaneswar RC group, please.
Okay.
You want book PDF or the PDF created by Gauri sir?
No, not Odisha. Mathematical physics by Satya Prakash.
Oh.
If anyone knows the question pattern of the passing mark, please share.
I think there will be 5 questions only, and question will contain 20 marks.
Can we get the PDF of today's class?
We are about to.
Anyone says the passing mark
We shall
of
let you
100
know.
marks exam? Please, anyone says the passing mark?
At least we need to score 50%, I think.
Okay.
Actually, 70% of the theory paper and 30% of the assignment mark is added, then it will be calculated. In IGNOU system generally, what I see in our BSc program. 70-30, and practical mark is differently.
प्रैक्टिकल मार्क तो ऐड होगा, परंतु जो थ्योरी पार्ट में 100 मार्क्स का होता है उसमें तो पास करना पड़ेगा ना, उसका पास मार्क कितना है?
हाँ, वो पास करना पड़ेगा। प्रैक्टिकल तो अलग होता है। थ्योरी का जो आप एग्जाम दोगे उसका 70% एड होता है। जैसे कि आप थ्योरी में 100 से 80 रखे तो उसका 8 आता 56 आता है, और असाइनमेंट में अगर उसमें 100 से 90 दिए होंगे तो 9 3 27, 56 और 27 को ऐड किया जाता है, और 100 से 36 रहता है उसका पासिंग मार्क। 100 से 36 होना चाहिए मिल के।
ओवरऑल पासिंग मार्क 36 है शायद।
असाइनमेंट से 30% और थ्योरी से 70% एड होके ऐसे हिसाब होता है। कैलकुलेशन होने के बाद वो पासिंग मार्क हिसाब होता है। 36 से अबव होना चाहिए। यही तो है 100 से 36 की थ्योरी।
Then how credits are actually given? Actually, the 2 credits will be awarded to everyone who will qualify, or on the basis of percentage they score in the examination.
Sorry, again you please say. 2 credits. 2 credits papers are
Those 2
generally 25
credits.
marks. 2 credits means?
Yeah, 2 credits whether will be awarded to everyone, or everyone those who will pass, or only for those who will score a minimum percentage.
No, credits means the books would consist of 2 credits, that is 25 marks. 4 credits, that
Right.
is 50 marks. 8 credits, that is
Right.
100 marks. And you have to
Okay.
follow the exam. It is equal for everyone.
Everyone. Okay. Those who will pass, they will be awarded with 2 credits.
No. It's a credit means the importance given to that means subject. Means suppose MPH-1 is 4 credit, That means a
credit
100
means
marks a
only
question should
books.
be.
That is MPH
Not
001. That
say
is four
actually marks.
credits.
Suppose it is
Okay.
having 4 credit means it will be 100 marks.
Okay.
Credit
Yes,
means
yes,
it is
yes. I think so.
hmm.
I think so.
Four
That
So
credits
means
means four
that
books.
means
accordingly, if it is
Four books
100
are
marks,
there.
the books will be more
that
simply.
that
It
is the
can be 3
question
books, it
that
can be 1 book
whether
also.
No,
okay.
here
Because,
credit means not the reward. Credit means the books, number of books.
no,
Suppose block
no.
1, block 2, block 3, block 4, that is 4 credits in
No, no, not
MPH
like that.
001.
See, if you will
Okay.
take in
No,
that
not no,
way,
no, no, brother. Not
your
like that. Not like
practical
that.
is only having 1 book, then how it is 4 credits. So it depends upon the
Yes,
importance given to that paper. Like 100
yes,
marks is 4 credit.
yes, yes. So our 2 credits
And
मतलब 50
in
marks.
order to pass a PG course, you need to minimum appear 24 credits.
Okay. Thank you. Thank you.
There it is. There are 14 days practical also for the practical schedule. So when it will be conducted, it will be by the RC. And it should be conducted during summer vacation, I think.
Summer vacation is already about to finish.
Please repeat. I can't hear.
Can anyone clarify whether 4 credits is 100 mark or 50 marks?
Hello? Yes, ma'am, 4 credit is 100 marks. 2 credit is 50 marks.
Yes, yes. 4 credits means 100 marks and 2 credits means 50 marks.
Guys, should we wait or leave the session?
ଏବେ 5ଟା ହେଇଗଲା ବୋଧେ ଆଉ ଜଣେ ସାର୍ ଆସିପାରନ୍ତି।
Next class କଣ 2 ଅଛି ନା 3 ଅଛି ଦେଖିକି ଟିକେ କହିବେ।
The only thing we can do is wait. Just.
Or write a mail to the RC. RC side classroom RC.
Yes, yes, you can do.
Hmm. Let's wait for another 10-15 minutes. Let's see. There may be a power failure. There may be something else in SARS area.
ଜ୍ୟୋତି ବାବୁ ଅଛ କି?
ବାଲେଶ୍ୱର FM କଲେଜରେ କେହି ଏକ୍ଜାମ ସେଣ୍ଟର ଦେଇଛନ୍ତି କି?
I think sir joined again.
There is an interruption. Okay. So pardon for that. So I think now the screen is visible. And I think the participants will be same for 5 to 6 p.m. class. So let us continue it. And then we'll go to the next part. So we are discussing Frobenius series method. So now I think the screen is visible.
Yes, it is visible.
Okay, okay, ठीक है.
Yes,
So
it is visible. Can you get the PDF, sir, of its
yes,
handwritten?
yes, definitely, definitely. It is made for you only.
Okay, okay, sir. Okay, sir.
So outlines of Frobenius method. So suppose you have a differential equation in a standard form y double dash x plus px y dash x plus qx yx is equal to 0. Y double dash x मतलब d square y by dx square. Y dash मतलब dy by dx. So first, in the first step, you have to write down the differential equation in the form y double dash x plus px y dash x plus qx yx is equal to 0. If you have any coefficients y double dash x, then just divide it to all the terms and you will have coefficient of y double dash x is equal to 1 and you have coefficients of y dash x and yx and you write them as px and qx. In the second step, from the behavior of the coefficients, now you see whether px and qx are analytic or not. In the second step, you just see whether px and qx are analytic or not. From that, you will decide whether to solve it or not. So you have to see whether at point x is equal to 0, it is an ordinary point or a regular singular point or essential singular point. In the second step, if it is ordinary singular point or ordinary point, then you go further. If it is essential singular point, you cannot solve it either by Frobenius method or by power series solution. In the third step, assume the solution in the form of extended power series or Frobenius series. So you have to write the solution will be in the form yx is equal to x to the power k summation n is equal to 0 to infinite an x to the power n, where the exponent k and the coefficients n are to be determined. We assume that the coefficients of the lowest power of x is non-zero. That is a0 is not equal to 0. Okay. So now write it in extended power series. In the next step, differentiate the assumed series solution term wise to obtain y dash x and y double dash x. Then substitute the resulting series for yx, y dash x and y double dash x in the differential equation. Okay. In the third case, differentiate it and get your yx, y double dash x, y double dash x and substitute it in the original equation. In the fifth step, combine the like powers of x and equate the coefficients of each power of x to 0. अब x का जो कोफिशिएंट जहां जहां x है उसको एक जगह ले लीजिए, जहां जहां आपका x डैश है वहां उसको एक साथ ले लीजिए, x स्क्वायर है एक साथ ले लीजिए, x क्यू है उनको एक साथ ले लीजिए, अलग अलग कर दीजिए. Okay. Then obtain the indicial equation by equating the coefficient of lowest power of x. अब जो टर्म आएगा लोएस्ट पावर x जो आपका एक्सप्रेशन में मिलेगा उसका जो कोफिशिएंट है वो उससे आपको इंडिशियल इक्वेशन मिलेगा. दिस इक्वेशन इन्वॉल्व्स द अननोन एक्सपोनेंट k. अब इस इंडिशियल इक्वेशन में जो k वैल्यू है उसको आप निकालिए by solving the initial equation. The roots of the initial equation give the possible values of exponent k, which in turn determine the nature of the solution of the differential equation. अब k के वैल्यू जब आपको निकाल दिए, अब नेक्स्ट हायर पावर को जाइए और वहां से कोफिशिएंट्स निकालिए, a1 क्या है, then a2 क्या है, then an क्या है, इस तरह से निकालना है. For each value of the exponent k, obtain the recurrence relation among the coefficients n by equating the highest power of x to 0. अब जो हाईएस्ट पावर है उसका जब कोफिशिएंट आप इक्वेट करेंगे, जीरो करेंगे, वहीं से आपको रिकर्सन रिलेशन मिलेगा जो हमको पावर सीरीज में मिला था. एक बार आपको रिकर्सन रिलेशन मिल गया तो you can solve it and get all the coefficients. Then substitute in the next step, step 5, substitute the values of the coefficients of an in the assumed solution. अब solution में an का value जो मिला है different value, substitute them. Check that the solution satisfy the original differential equation. अब check कीजिए ये original differential equation satisfy करता है या नहीं करता है. In the last step, check the convergence of the series obtained above. Now illustrate an example. एक example देके अब देखते हैं कैसे step by step हम करते हैं solve एक स्पेशल फंक्शन को. सपोज हमने पहले जो किया था सिंपल हार्मोनिक ऑसिलेटर वाला प्रॉब्लम उसी को दोबारा करते हैं फ्रोबेनियस मेथड में. So you have xt is equal to in extended power series t to the power k summation n is equal to 0 to infinite a n t to the power n where a0 is not equal to 0. This is equation 3.16 where the exponent k and the coefficients n are to be determined. Term-wise differentiation yields x dash t is equal to summation n is equal to 0 to infinite a n multiplied by n plus k t to the power n plus k minus 1. Similarly, x double dash t is equal to summation n is equal to 0 to infinite a subscript n multiplied by n plus k multiplied by n plus k minus 1 multiplied by t to the power n plus k minus 2, equation 3.70. Now substitute these two values, x double dash and x dash, in the original equation, and you will get summation n is equal to 0 to infinite a subscript n multiplied by n plus k multiplied by n plus k minus 1 multiplied by t to the power n plus k minus 2 plus omega square, which is the omega is the angular frequency, multiplied by summation n is equal to 0 to infinite n t to the power n plus k is equal to 0. Now increasing the summation index by 2 and simultaneously decreasing the starting point by 2 in the first term, we get summation n is equal to minus 2 to infinite a n plus 1 a subscript n plus 2 whole multiplied by n plus k plus 2 multiplied by n plus k plus 1 multiplied by t to the power n plus k plus omega square summation n is equal to 0 to infinite a n t to the power n plus k is equal to 0. Now you can write it as a0 multiplied by k minus 1 multiplied by t to the power k minus 2 plus a1 multiplied by k plus 1 multiplied by k multiplied by t to the power k minus 1 plus a n is equal to 0 to infinite a n plus 2 a subscript n plus 2 multiplied by n plus k plus 2 multiplied by n plus k plus 1 plus omega square a n whole multiplied by t to the power n plus k is equal to 0, equation 3.18. Now the coefficients of each power in the above series must vanish individually because t to the power k minus 1, t to the power k minus 2, t to the power n plus k, these are non-zero. So obviously the coefficients will be 0. So first what to do in the outline we have seen. See your combine like powers हो गया, like power 5 वाला जो है. Then आपका 5a देखिए इंडिशियल इक्वेशन कैसे निकलेगा. जब लोएस्ट पावर ऑफ x को पहले हम क्या करेंगे, डिफरेंशिएट करेंगे, इक्वेट करेंगे, ऑब्टेन द इंडिशियल इक्वेशन बाय इक्वेटिंग द कोएफिशिएंट्स ऑफ लोएस्ट पावर ऑफ x. ठीक है, पेज 169 में 5a में हमने दिखाया आपको. अब यहां देखिए लोएस्ट पावर कौन सा है, यहां लोएस्ट पावर है कौन सा, t to the power k minus 2. So coefficient of t to the power k minus 2 will give your initial equation. So coefficient of k minus t to the power k minus 2 will be a0 multiplied by k into k minus 1 is equal to 0. So this is the initial equation. Now solve it. Your a0 is not equal to 0. The roots of the equation are k into k minus 1 is equal to 0. So k is equal to 0 or k is equal to 1. So there are two roots. One is 0, another is 1. Because a0 is not equal to 0, we have assumed it in the first case, at the early stage. First we have assumed that a0 is not equal to 0. So your rest will be 0. So your solution will be, the roots will be k is equal to 0 and k is equal to 1. So now equate the next term. From initial equation you get the values of k. Now put these values of k in the next higher term. So equation 3.18 जो है इसमें next higher term क्या है t to the power k minus 1 t to the power k minus 1. अब इसका कोफिशिएंट क्या है a1 multiplied by k plus 1 multiplied by k. So your t to the power k minus 1 is non-zero. So obviously your a1 k multiplied by k plus 1 is equal to 0. So if k is equal to 1, then k into k plus 1 is equal to how much? If k is equal to 1, if k is equal to 1, your 1 multiplied by 1 plus 1, 2. So 1 multiplied by 2, that is 2. So your k into k plus 1 is equal to 2, that is non-zero. So if k into k plus 1 is non-zero, then obviously a1 is equal to 0 because the whole term will be 0. So this is your a1 is equal to 0 or k is equal to 1. If k is equal to 0, then 0 multiplied by 0 plus 1. So 0 multiplied by 1 is equal to 0. So your k into k plus 1 term will be 0. So if it is 0, then a1 may be 0, may be non-zero. Because k into k plus 1 is equal to 0 means the whole term in the second term will be 0. So it does not depend upon the value of a1, whether it is 0 or non-zero. So hence, the value of a1 is arbitrary. It can be 0 or non-zero. Equating the coefficients of x to the power n plus k, you can get the recursion relation. That is the highest power in the equation 3.18c, page 170. So the coefficients of t to the power n plus k will be how much? A to a subscript n plus 2 whole multiplied by n plus k plus 2 whole multiplied by n plus k plus 1 plus omega square an is equal to 0. So your n plus 2 is equal to minus omega square divided by n plus k plus 2 whole multiplied by n plus k plus 1 whole multiplied by an. So this is the recursion formula and can be used to evaluate the coefficients an. Okay, so how can you get the coefficients? Now the roots for the initial equation, that is k is equal to 0, k is equal to 1. Now put it in equation and solve equation 3.21. So for case 1, k is equal to 0. In this case, the recursion relation given by equation 3.21 becomes a subscript n plus 2 is equal to minus omega square divided by n plus 2 multiplied by n plus 1 whole multiplied by n, equation 3.22. Now, starting from a0, we can get even coefficients. That is, for n is equal to 0, you will get a2 is equal to minus omega square divided by 2 multiplied by 1 a0, that is minus omega square by 2 factorial a0. This has also we have obtained from power series earlier. So similarly, n is equal to 2, a4 is equal to minus omega square by 4 multiplied by 3 whole multiplied by a2, that is a to the power, omega to the power 4 divided by 4 factorial a0. See, your a2 can be written as minus omega square by 2 multiplied by 1 a0. So put it here, you will get minus omega square multiplied by minus omega square, that is omega to the power 4. In the denominator, 2 multiplied by 1 multiplied by 3 multiplied by 4 is equal to 4 factorial. So you have omega to the power 4 by 4 factorial a0. Similarly, for n is equal to 4, your a6 is equal to a subscript 6 is equal to minus omega square by 6. Is the screen visible?
ନାଇଁ ସାର୍ ଦେଖା ଛୋଟ ଛୋଟ ଅକ୍ଷର ରହୁଛି ନା ଦେଖା ହଉନି ଜମା।
ଆଚ୍ଛା ଆଚ୍ଛା ଆଉ କଣ କରିବା?
ଏ ମେଟେରିଆଲ ଟା ଅନ୍ୟ କୋଉ ଜାଗାରେ ଅଛି କି ସାର୍? କୋଉଠୁ ମାନେ
ଦେଖ ଖୋଜ କୋଉଠି ଯଦି ଥିବ ନହେଲେ ଆମେ ଦବା ଆଉ। এটা ମୋର ନିଜ ମାତ୍ରା।
No, you can zoom your screen. You can zoom your screen. If it's not visible, you can zoom your screen.
So a6 is a subscript 6 is equal to minus omega square by 6 multiplied by 5 a4. So put the value of a4, that is omega to the power 4 by 4 factorial a0, and you will get minus omega to the power 6 divided by 6 factorial whole multiplied by a0. So the general term with even coefficients can be written as a subscript 2n is equal to minus 1 to the power n whole multiplied by omega to the power 2n divided by 2n factorial whole multiplied by a0. Similarly, you can have the odd coefficients by putting what? Case 2. Case 2 में आपको odd coefficient मिलेगा. So before going to case 2, from equation 3.20 we get a1 k into k plus 1 is equal to 0. For k is equal to 0, the coefficients is a1 is arbitrary, which we can set equal to 0 for a convenience. With this choice, the two terms recursion relation of equation 3.22 implies that all the odd coefficient vanish. That is A1 is equal to A3 is equal to A5 is equal to 0. So substituting K is equal to 0, you can have A1 plus A3 plus A5, so on and so forth is equal to 0. And equation 3.23 and in equation 3.16 we get xt is equal to x, which is a function of t, is equal to A0 plus A2 t square plus A4 t to the power 4 plus so on and so forth, A subscript 2n multiplied by t to the power 2n, so on and so forth. You can get A0 whole multiplied by 1 minus omega square by 2 factorial whole multiplied by t square plus omega to the power 4 t to the power 4 by 4 factorial plus so on and so forth minus 1 to the power n omega to the power 2n divided by 2n factorial t to the power 2n plus so on and so forth, or x1t is equal to A0 cos omega t. Okay, so this is the cosine term which you have already obtained in power series solution. So if k is equal to 1, similarly you can have the recursion relation a n plus 2 is equal to minus omega square by n plus 3 multiplied by n plus 2 whole multiplied by an. Since k is equal to 1, equation 3.20 implies a1 is equal to 0. So the recursion relation equation 3.25 implies a1 is equal to a3 is equal to a5, so on and so forth is equal to 0. On the other hand, a2 is equal to minus omega square by 3 factorial a0, a4 is equal to minus omega square by 5 multiplied by 4 whole multiplied by 2, that is omega to the power 4 by 5 factorial whole multiplied by a0, and you have x2t is equal to a0t plus a2t square plus a4t to the power 5 minus so on and so forth. So this is a0 by omega sine omega t, because omega t minus omega square q t q by 3 factorial plus omega to the power 5 t to the power 5 by 5 factorial. This is nothing but the series expression of sine omega t. Now the two series given by equation 3.24 and 3.26 converge for all finite values of t, because sine function and cosine function both are convergent for all values of t. Both the solutions satisfy the differential equation given by equation 3.10. So each is a valid solution of the given differential equation. Further, the Roxian of the two solutions x1t and x2t can be written as w is equal to x1t determinant of x1t, x2t, x1 dash t, x2 dash t, that is a Roxian determinant of a0 cos omega t, a0 by omega sine omega t minus a0 omega sine omega t, a0 cos omega t. So the two solutions are linearly independent because the determinant is non-zero, 3.28. If you find out the values of the determinant, it has a finite value, it is not 0. So since the Roxian is non-zero, that is not equal to 0, the existence of a linearly independent solutions were expected because x is equal to 0 is an ordinary point of the equation 3.10. So you see, in any equation, if the Roxian is 0, that is linearly dependent. If Roxian is non-zero, that is linearly independent. So in this case, since the Roxian is non-zero, it is linearly independent. So there is some examples, you may go through it. Okay. So now you just go through this material. So shall I put it in which WhatsApp group?
Sir, you are added only in two WhatsApp groups, sir.
Sir, put it in Igno official. I think that is having around 500 subscribers.
Just go.
What's going on?
After 2 to 3 minutes, you can start the use of this place. After 2 to 3 minutes,
Mute
you just
yourself.
recollect and think about power series and programming this method.
Indranil sir, please. Is it the end of the class? Sir has left already.
He is there.
କ୍ଲାସ୍ ଆଉ ହବ ନା ହବନି?
ଆଉ କ୍ଲାସ୍ ହବ ବୋଧେ 5ଟାରେ ହବା କଥା।
I think there will be no class.
हम लोग कॉल से निकल जाए क्या?
अरे म्यूट करो सब।
सर सुना होनी किसी।
Okay, sorry, it was muted. Okay, so now let us have Bessel's function, Bessel's differential equation and Bessel's function, page 54 of your study material, page 54. So Bessel's function of first kind, that can be written as x square d square by dx square plus x dy by dx plus x square minus m square yx is equal to 0. So we have written that x square y double dash plus x y dash plus x square minus k square y is equal to 0. So in case of k, he has taken m in the original equation and others are same. So our Frobenius method, we have discussed how we solve it by extended power series. So so the expression here, it is written as yx is equal to summation n is equal to 0 to infinite a subscript n x to the power x n plus r. So we have k, here it is r, all other things are similar. Okay, in place of k, it has taken r. So you have to solve for r. We have taken the value of k is equal to 0 and 1 in the earlier case. Here you will have to find out the value of r and then you will solve it. So see, then they have solved by using only 3 equations and 1 page. But you can have it a detailed derivation as I have shown you in the previous class, and you can have the recursion relation and solve it. Okay. So he has taken gamma function, gamma m plus 1 plus m gamma m. So a0 is equal to 1 by 2 to the power m gamma m plus 1. So solved it, and y1 is equal to jmx is equal to summation k is equal to 0 to infinite minus 1 to the power k 1 by k factorial gamma m plus k plus 1 multiplied by x by 2 to the power 2k plus 1. This is the Bessel's function of first kind. Then you have the y2. We have solved for x1 and x2. It is here, it is solved for y1 and y2. For y2, it is j minus mx is equal to summation k is equal to 0 to infinite minus 1 to the power k 1 by k factorial multiplied by minus m plus k plus 1 whole multiplied by x by 2 to the power 2k minus m. So this is order minus m, in the first case order m. So now the solutions are jn is equal to what? Jn is equal to y1 plus y2. That is k is equal to 0 to infinite minus 1 to the power k 1 by k factorial gamma n plus k plus 1 whole multiplied by x by 2 to the power 2k plus n is equal to summation k is equal to 0 to infinite minus 1 to the power k 1 by k factorial n plus k factorial x by 2 to the power 2k plus n, and your n plus k plus 1 is a positive integer, and gamma n plus k plus 1 is equal to n plus k factorial. So now the j0, j1 and j2 are expressed like this and plotted as shown in figure 3.1. The values of x for which the Bessel functions become 0 are set to the zeros of Bessel function. And your x is equal to 0, j0 x is equal to 1, and j1 x as well as j2 x are indeed higher orders of Bessel functions are 0. This readily follows the series given by equation 3.6. Now, as x tends to infinite, we obtain jnx, which corresponds to the first term with k is equal to 0. So your jnx is equal to tends to 1 by n factorial x by 2 to the power n, where x tends to 0, and j minus nx is equal to summation k is equal to 0 to infinite minus 1 to the power k 1 by k factorial gamma minus n plus k plus 1 multiplied by x by 2 to the power 2k minus 1. Now put this result and you can find out the values of jn. Now the recursion relation will be written in 3.2.1, and you have m by x multiplied by jmx minus djm by dx is equal to jm plus 1x, equation 3.10. And now the derivatives resultant expression, the derived derivative term will be jm minus 1, and it is 2 j dash mx. Now the generating function of the Bessel's function of first kind and integral order is given by g x comma t is equal to exponential x by 2 t minus 1 by t, which is equal to summation n is equal to minus infinite to infinite j n x t to the power n. Now you solve it and you can find out jn minus 1x plus jn plus 1x is equal to 2 n by x jn x, and this is the same recurrence relation as given is in equation 3.11. So there are some examples of Bessel's equation, and the Bessel functions of first kind j0x j and jnx are written as 3.15a, 3.15b, and 3.15c. Okay. Now the Bessel's function of second kind can be written like this as equation 3.16a, that is also called as Weber function, named after Heinrich Martin Weber, and with notation ynm, that is Neumann function named after Carl Neumann, and equation 3.16b. Then the figure 3.5 plots of Bessel function of second kind of the order 0, 1, and 2 is written as y0, y1, and y2. Then spherical Bessel function, you can write it in spherical polar coordinates. The Helmholtz equation r square d square r by dr square plus 2r d capital R by d small r plus k square r square minus n into n plus 1 r is equal to 0. Now you solve it and you can have your jn is equal to root over of pi by 2x jn plus 1 by 2x is equal to equation 3.25, and the plots of spherical Bessel function are shown in figure 3.6. So one thing I can do, the IGNOU will send you the general method of solution which I have discussed earlier, and you try to solve it, because in this material many steps are being omitted. So you just go through the basic outline of the Frobenius method and you can easily solve and arrive at the final expression given from given in the study material from page 54 to 68. So first kind you can get, and others you can also solve and also go through the examples. So the study material, you just go through the examples, worked out exercises, but so far as derivation is concerned, try to work out the each step by using the general Frobenius method. And if by 4 p.m. tomorrow you could not get it, don't worry, I shall also put the detailed steps how to solve this material, because I think first you try. If you fail, then you can go through the material which solve all these steps in between tomorrow. Okay. But so far as exercises are concerned, examples are concerned, you must go through the study material in detail, and you will have some of the problems and maybe all the problems from this material. Then the next is Legendre polynomial. See, I have told in my previous class from 4 to 5 that Legendre differential equation can be written as 1 minus x square y double dash minus 2xy dash plus L into L plus 1 y is equal to 0. Here it is written as 1 minus x square y double dash minus 2x y dash plus n into n plus 1 y is equal to 0. Equation 4.1, page 76. So first term is same, 1 minus x square y double dash. Second term is same, 1 minus, minus 2x y dash. But in the third term, I have taken the constant as L into L plus 1 y. The study material, you have n into n plus 1 y. So n and L both are constants. Okay, so I have taken L. The notation the writer has taken is n. So there is no problem, I think. Okay, so n into n plus 1 y, equation 4.1. In the material which Dr. Panigrai sir let you forward will be L into L plus 1. So yeah, as both are constant, L is a constant, n is a constant, just the notation is different, so both are same. So now this can be solved by using Frobenius method. Okay, so y is equal to a0, shown as shown in figure 4. Equation 4.2. A0 1 minus n into n plus 1 2 factorial multiplied by x square, then so on so forth, plus a1 x minus so on so forth. This is written here. And you have y is equal to a0, y is equal to a1x, when n is equal to 1, y is equal to a0 1 minus 3x square, when n is equal to 2, y is equal to a1 3x minus 5x cube by 2 when n is equal to 3. This is Legendre polynomial p and x. Okay, all these values. So you have a Legendre function of second kind as shown in figure 4.6, and you have the recursion formula for Legendre equation as shown in 4.5. Recursion formula, you know how to get the recursion formula. First take the lowest power, then get the initial equation, then the higher power, then the highest power will give you the recursion formula. And all these steps you can work out, because here only final recursion formula is given in page 76, but you have to solve all this, and if you fail, then I can supply you the detailed step tomorrow before or around 4 p.m. So your a k plus 2 is equal to minus n minus k multiplied by n plus k plus 1 divided by k plus 1 multiplied by k plus 2 whole multiplied by ak, for n is equal to 1, 0, 1, 2, so on and so forth. As shown in figure 4.5, this is the recursion formula. And from the recursion formula, you can find out a1, a2, a3, so on and so forth, as shown in equation 4.7. Then your generating function, gx comma t is equal to 1 minus 2xt plus t square to the power minus half is equal to summation n is equal to 0 to infinite p n x t to the power n. Okay, now we can expand it by binomial expansion, and you have 1 plus xt plus half 3x square minus 1 t square plus half 5x cube minus 3x t cube plus so on and so forth. And equating the coefficients of t to the power n for n is equal to 0, 1, 2, 3, as we have derived from the initial equation the values of n, and we find the few Legendre polynomial as p0x is equal to 1, p1x is equal to x, p2x is equal to half 3x square minus 1, p3x is equal to half 5x cube minus 3x, so on and so forth. Okay, so this is the generating function for Legendre polynomial. Then your recursion relation can be written as gx comma t is equal to 1 by root over 1 minus 2tx plus t square is equal to summation n is equal to 0 to infinite p n x t to the power n. Now differentiate it del g by del t, partial differential equation, you can have n is equal to 0 to infinite n p n x t to the power n minus 1. And the final expression as shown in equation 4.14, 2n plus 1 x pnx minus n plus 1 pn plus 1 x plus n pn minus 1 x. This is one of the two important recursion relation and correlates any Legendre polynomial with the adjoining polynomial. So, for example, by putting n is equal to 1, you can get 3x p1x is equal to 2p2x plus p0x. But we know that p0x is equal to 1 and p1x is equal to x. So we have 3x square is equal to 2p2x plus 1, and p2x is equal to half 3x square minus 1. Similarly, p3x can be obtained using expression for p1x and p2x, and p4x can be obtained using expression p2x and p3x, and so on. To derive the second recurrence relation, we differentiate gx comma t partially with respect to x, and you can get del g by del x is equal to summation n is equal to 0 to infinite p n dash x t to the power n. So you have 0 to infinite summation 0.
କ୍ଲାସ୍ ସରିଗଲା ନା କଣ? କ୍ଲାସ୍ ସରିଲାଣି ନା?
କ୍ଲାସ୍ ଆଉ ହବ ନା ସରିଗଲା?